think there's a question on the study guide that asks, why is it hard to treat diseases that have misfolded proteins?
Yeah. Is that in the book?
This is how Brother Lemon taught it. He gave us this chart, and it's not really technical, but it's like this folding funnel. And so on the bottom, number of conformations. And then on the top is your energy level. So here's like right after you make your protein. So most of your proteins are just long polypeptide strands, right? And so any slight, tweak in it would give it a different conformation. So there's a lot of different conformations they can be. But as they start to fold, they're all going to fold to one specific properly folded protein. They're just going to have one specific conformation, like we think of our protein. But some of them will misfold, and they might be folded wrongly. And the proper folding will have the lowest energy, be the most stable. If it's misfolded, it will be less stable, but to get it to the right conformation, it has to unfold and then refold. So there's kind of this hill.
Yeah, I know what you're saying.
There's like this energy
barrier.
Yeah.
Mm-hmm.
And so in order to get it to this point, you'd have to put in energy so it would unfold and then refold. So it's really hard to get them folded properly, because you can't just add a medicine that will say, hey, let's untwist this and then retwist it this way. So.
That makes sense.
And because they're going to be locked in by hydrogen bonding and these interactions there, so you'd have to break those.
So you can't. So basically, what you're trying to say is you just can't. You can't undo what's already been done.
You can't. It just requires a lot of energy. It's not like, oh, I'm folded wrong here. Well, I just folding properly is lower energy. It is. There's like this activation energy.
Oh, okay.
Some proteins though, it's really easy to get over that hump, but other proteins, it's more difficult.
And so with the more harder to treat diseases, it's from the proteins that require high activation energy.
And I don't know if it's technical to call it activation, just there's this energy barrier and how it's folded. And that's the thing with Alzheimer's. There's a really cool video clip. It shows how the Alzheimer's protein has these alpha helices. What happens is protein in your brain, something causes these helices to unwind and become beta sheets.
Prion.
Yeah. Mm-hmm. And so that's what causes Alzheimer's, is helices turning into beta sheets, and then they just stack on top of each other because beta sheets are flat. So then you just get this buildup of these prions, and so you can imagine to change that back from a beta sheet to a helix would require a lot of energy, and that's what we're trying to figure out, is how to do that.
That's pretty cool.
Huh.